Hello everybody. This lesson is on Newton's law of, wait, I'm trying to be fancy. It's not working. There we go. Newton's law of universal gravitation. So some of the information that you should already understand before we talk about this topic is first, weight. We know that the weight of an object is equal to its mass times gravity. And we also know that as an object moves throughout the universe, its mass remains the same no matter where it goes. This is the mass moving through the universe, if you couldn't tell. We also know that mass is measured in kilograms, and weight is measured in newtons. The weight of the object, which is represented with F of g, is also called a force of attraction. It's how your mass is attracted to the Earth. Your weight is a result of your mass multiplied by the acceleration due to gravity, 9.81, and that is the force of attraction between you and the Earth. In this lesson, we're going to talk about Newton's law of universal gravitation. It's another way of determining the weight of objects no matter where we are in the universe. It exists between any two spherical bodies, and we don't have to be spherical because we can consider ourselves as a center of mass, a point of a center of mass, and we can consider ourselves as a spherical body. It works pretty well. The equation works pretty well with non-spherical bodies as well. The best example that I can give you of Newton's law of universal gravitation is that of the Earth and the Moon. The Moon revolves around the Earth in a circular path. In order for the Moon to revolve around the Earth in a circular path, it needs to be constantly pulled inward towards the Earth. There is a force of attraction between the Earth and the Moon that is equal and opposite. As we talked about with Newton's third law, even though the forces are equal, the actions are different. So our smaller moon would have a greater acceleration towards our Earth than our Earth towards our moon. There's a great difference in mass. Anyway, as a result of this force of attraction, the moon is pulled inward towards the Earth's center. And as a result, we have the moon revolving around the Earth in this orbit. This force of attraction is what we call F of g. Newton understood that gravity was responsible for not only having, say, apples fall to the ground, but also for the movement of celestial objects, like the moon orbiting around the Earth, or the Earth orbiting around the sun. But he didn't know how it worked. And it wasn't until much later after his death that more of this theory developed. Henry Cavendish played with an experiment to show that two spherical masses do move towards one another, are attracted to one another. So I have a video of the Cavendish experiment in a time lapse so that they can speed it up because it takes a very, very long time. And so this theory was further developed by Cavendish, and mathematically they found that there was a constant of proportionality that had to be there mathematically in order for the equation to work. And we call this constant the gravitational constant, or universal gravitational constant. The universal gravitational constant, big G, is found on your reference tables as 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. And yes, you have to write all of that when you substitute in with units. Now let's watch the Cavendish experiment. Unfortunately, the video won't play and through this video recording, so you do need to open up the YouTube page, and you can simply search for Cavendish experiment / time lapse, and it should come up. I know you guys must be jumping out of your seats with excitement over that experiment, but the interesting part is that the masses on the rod were attracted to those large rocks. There's no outside forces other than the force of gravity between the two masses. There's no magnets, there's nothing other than the force due to gravity causing that motion that you saw. So, actually, it was pretty cool, considering how boring it was at the same time. So how do we relate all of these concepts together in one formula? So the formula that Cavendish was working on was that these two spherical bodies, they attract each other with this force, which is proportional to the product of their masses. So it had directly related to the mass of the spherical bodies. And it was inversely proportional to the square of the radius between them. So, in other words, if these objects are more massive, then it's going to have a direct relationship on the force of attraction. So, the more massive the objects are, the greater the force of attraction. And it also was inversely proportional to the distance between the two masses. So if the masses were separated by a large distance, the force of attraction was very weak. However, when those two objects became closer and closer to one another, the force of attraction increased exponentially. So what I would like you to do is use the definition to create a formula for this theory. You can pause the video now to create your formula in your notes. So what did we come up with? You should have come up with that the force of gravity, F of g, is directly related to the product of both of the masses, A and B, or 1 and 2, depending on what you prefer, and inversely proportional to the distance between them squared. This is what Newton had discovered, but there was something missing that Cavendish was able to add to this formula. Cavendish added the universal gravitational constant, g. And it is a constant of proportionality in order for this side of the equation to balance this side of the equation. As I noted earlier, big G can be found on your reference table as 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. So, again, universal constant is a value that balances the formula relating the force of gravity, mass, and distance between two objects. So I have this little story to help you remember this inverse squared law and how the masses work in relationship to the force of attraction as well. So let's say you have Sally. Sally is a senior in high school, and Sally is madly in love with Sam. So Sally, and here's Sam. And they're going out and they have a great relationship. They're in love and they're high school sweethearts, and they plan on staying together after high school, and they go off to college. Okay, so Sally and Sam go off to college, and what happens? Oh, they move far apart, and they don't really like each other as much as they thought anymore. So the force of attraction between them decreased. So as they moved far and far away from each other at their different colleges, the force of attraction between them decreased. Here's another thing that happened. Well, when Sally and Sam went off to college, they gained their freshman 15. And now, coming back home, not only did they gain their freshman 15, but they also are coming home for Thanksgiving break. So they have more mass, and they have less distance between them, and they are totally in love with each other once again. So that is the story of Sally and Sam, and it also tells you about the relationship between the force of attraction. When two objects are farther away, the force of attraction decreases exponentially. And when the two objects are closer together, the force of attraction increases exponentially. And if the masses increase as well, the force of attraction also increases. And Sally and Sam will live happily ever after. Also, some of you may be wondering about why the distance between the two centers is called a radius. So, to explain this, I drew the Earth and the Moon. And the distance between their centers is this distance here. But typically we don't call it D, we call it R, because it is the radius of this larger circle of the Moon orbiting around the Earth. So that's why it's called a radius, because the smaller mass typically revolves around the larger object. The first thing we're going to do is find how much the child weighs on Earth. So we can do this two different ways. We can simply use the formula that we've been using to find weight, which is force of gravity, or weight is equal to mass times gravity. So if we know the child's weight, mass, 25 kilograms, and we multiply by gravity, 9.81 meters per second squared, then we will have the weight of the child, which is 245.25 newtons. But this is not the only way that we can calculate the weight of the child. The other way to calculate the weight of the child is to use the new formula you just learned. So let's use f of g is equal to g m1 m2 over r squared. So the tricky thing with this formula is figuring out what masses to use. We're finding the weight of the child. We'll use the universal gravitational constant, the mass of the child, and the mass of the Earth, because the child is standing on Earth. We're also going to use the mean radius of the Earth, because that is the distance between the two objects. Okay, so now we're ready to substitute in. The force of attraction or force of gravity for the child on the earth is the universal gravitational constant, which is 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. And then we're going to multiply this by everything in parentheses here. And I ran out of room, so I'm going to put it below. So the mass of the child, actually let me try to move this around for you. So the mass of the child is 20. We have 25 kilograms. The mass of the Earth on your reference tables is 5.98 times 10 to the 24th kilograms. And then all of this on top is in your numerator. All of that you'll be multiplying. And then the radius, mean radius of the Earth, you can look up on your reference table as well, is 6.37 times 10 to the 6th meters. And that you also have to square. That's basically the most common error, is that people forget to square the radius on the bottom. Sorry, that's a 3. So, go ahead and calculate the force of attraction for the child between the child and the Earth, and tell me what you get. Please make sure you pause the video so that you have time to calculate. Your answer should be 245.75 newtons. So when we compare this to Fg equals mg, it's just a little different than what we got before, where we got 245.25 newtons. This could be because of a rounding issue between the two different formulas. Okay, so now we have the force of attraction for the child, or his weight, on the Earth. And we found that 2 different ways. Next, we're going to find the weight of the child on the moon. We're going to do it with our new formula. F of g is equal to, for the child, is equal to universal gravitational constant, the mass of the child, the mass of the moon this time, and the mean radius between the child and the moon's surface, which is the radius of the moon, and that is squared. Okay, so here we go. We substitute in f of g is equal to 6.67 times 10 to the negative 31 newtons meters squared over kilograms squared. A little hard to use the stylus. The mass of the child, again, is 25 kilograms. And the mass of the moon we look up on a reference table is 7.35 times 10 to the 22 kilograms. We can look up the mean radius of the moon as well. And we get 1.74 times 10 to the 6th meters. Remember, we need to square that. Again, please follow the steps I gave you last time. You want to multiply everything on the top here, get an answer in your calculator or write it down, and then divide by the square of the bottom. Please pause the video now so that you can do your work in your calculator. The answer that you should get is 40.48 newtons. the next thing we can do is compare the force of gravity on Earth to the force of gravity on the moon. So, the force of gravity on the moon is 40.48 newtons, and the force of gravity on Earth is 245.75 newtons. Sorry about my handwriting. And we get 1/6.06. So that means that the force due to gravity on Earth is approximately 6 times greater. We can also determine the acceleration due to gravity on the moon since we know the weight of the object and the mass of the object. So, if you have the weight of the child on the moon, we can determine the gravity on the moon based on the weight. 40.48 newtons was the weight on the moon, divided by the mass of the child, 25 kilograms, will give you the acceleration due to gravity on the moon. So the acceleration due to gravity on the moon is 1.62 meters per second squared. Let's try another example. So we have two masses of 3 kilograms each, and they're separated by a distance of 3 meters between them. And we want to know the force of attraction between the two masses. Set up the formula. F of G is equal to G M1 M2 over R squared. We substitute in for G 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared times each of the masses. We have 3 kilograms for each object, and they are separated by a distance of 3 meters, which is squared. So this is a typical multiple choice question. If both of the masses are equal and the distance between the masses are the same value, then 3 times 3 is 9, and 9 on top and 3 squared on the bottom is also 9. These values all cancel. But so also do the units, so you do need to be careful there. And the force due to gravity, we don't need a calculator for, is 6.67 times 10 to the negative 11 newtons. And we're finished. We are now going to work on the equation manipulation worksheet. It is Conceptual Development Practice, page 13-2. We're going to be working with our formula. F of G equals GM1 M2 over R squared. So they have it labeled as D for the distance. We use R in Regents physics. So you can replace D with R in your worksheet. So for the first example, they talk about what would happen to the force due to gravity if one of the masses were doubled. So if we want to see what happens to the force due to gravity if one of our masses is doubled, then we just simply look at how our original equation, or the old equation, has changed. So really all we are doing is multiplying the entire equation by 2. Oh, I can't take that 2 out. I can try to move this 2 here. Nope, can't move it. And take this 2 out and bring it over here. This is our original equation, and now we have it multiplied by 2, which means that if we change the equation on this side by 2, then we have to change the equation on this side also by 2 in order for everything to be balanced. So you see on the paper that the new equation is 2 times the old equation. You don't have to use new and old. You can simply write it as I have for this example. Let's try the other example. In this example, we are going to be doubling the separation distance, or doubling the radius. So, if we multiply the radius by 2, however we change the radius also will need to be squared since the radius is squared. So if the radius were, say, 3 meters, and 3 meters needs to be squared, if we were to double 3 meters to make it 6 meters, then 6 meters would be squared to make 36. So whatever you do to the radius must also end up being squared. So mathematically, I'm going to show you one more step in between. They do the same in the worksheet, so you can follow. We have 4 r squared because 2 squared is 4. So now we can look at how our original equation changed. All I need to do is move that 1/4 out. This is the original equation, and this is how the factor by which it is changing. So what has happened to f of g? The force due to gravity or force of attraction has decreased by 4, or 1/4 the original amount. Whatever you have on this side, you have to balance on this side. Lastly, I just want to read to you number 6. Consider a pair of binary stars that pull on each other with a certain force. Would the force be larger or smaller if the mass of each star were 3 times as great when their distance apart is 3 times as far? Show what the new force will be compared to the first one. So in this problem, they want you to triple the mass of each of the stars. So you have 3 times the mass of each of the stars, and they also want you to triple the distance between them. Okay, so I just wanted to set you up for number 6. You can finish that. Now it is time to work on Prentice Hall. Page 52, the questions assigned. Please circle anything that you're going to need help with tomorrow. Please take your notes about gravitational fields. Now that you wrote down the notes, let me explain what you wrote down. So gravitational fields are only a way of displaying the gravity that exists around a spherical body. So if we look at the Earth, you can see that the gravitational field lines get closer together as you go towards the Earth. And I've denoted that with the separation distance here between the lines. As you go towards the object, the intensity of gravity becomes greater. So gravitational field strength is displayed by the relative distance between the field lines. So if we look at this drawing here, anywhere that the field lines are close together, such as in this space here, or this space here, anywhere close to the objects, the field lines are closer together. This would be where the gravitational field strength is the strongest. Wherever the field lines are farther apart, such as in this area here, or out in this general area here, the gravity or field strength is less. So it's just a way of representing the gravitational field strength as you near a large spherical body. We already know that when two objects are closer together, the field strength is greater. We know that because f of g equals g m1 m2 over r squared, that the force of attraction f of g has an inverse squared relationship with the radius or separation distance. So as the objects become closer together, the force of attraction increases exponentially. So we know that as we're getting closer and closer to the object, the force of attraction increases, and therefore gravity will increase. I'll rewrite this formula for you. G equals Fg divided by m. So as the force of attraction increases, gravity, the acceleration due to gravity, also increases, which is why in most of the problems you read, it says near the surface of the Earth, and what that means is that near the surface of the Earth, gravity is 9.81 meters per second squared, but as you move farther away from the Earth, gravity changes. Well, how does it change? Well, opposite of what we just said, as we go farther away, let me pick a different color. As the radius or separation distance increases, there's an inverse square relationship to the force of attraction, so it decreases exponentially. So if the force of attraction is less, then gravity will become less. So gravity decreases as you move away from the surface of the planet or spherical body. Let's try this problem. It's kind of hard to see, so I'll read it to you. In which diagram do the field lines represent the gravitational field around the Earth? So, we just saw a picture in our notes. We know that as you become closer and closer to the object, you're pulled towards it. So the field lines should be going in towards the Earth. That leaves us with two choices, 1 and 4. But the field lines around the Earth are directed straight in towards the center of the Earth. It's how we would be pulled if we were standing on the Earth's surface, which is directly inward towards the center of the Earth, just like you learned with weight. So the correct answer is 1. You might be thinking of different field lines when you're looking at choice 3 or choice 4. The field lines you might be thinking about are magnetic field lines, which we'll talk about a little bit later in the year. Let's work on some of the checkpoint questions that I have for you. I'll help you through them. It says, when Earth and Moon, that gives us some information. We can look up the mass of the Earth and the mass of the Moon on our reference tables, are separated by a distance of 3.84 times 10 to the 8th meters. That is the separation distance r. So I can look up the mass of the Earth, I can look up the mass of the Moon, and then this would be r, the separation distance between them. The magnitude of the gravitational force of attraction between them is 2 times 10 to the 30, that's a 30 newtons. So that's F of G, force of attraction. What would be the magnitude of this gravitational force of attraction if Earth and Moon were separated by a distance of 1.92 times 10 to the 8th different separation distance? The best way to tackle this problem is to see how the radius changed. So, what happened to the radius? Was it doubled? Was it halved? Was it tripled? Was it quadrupled? So, compare the two radii, and then you'll know where to go with the equation manipulation. Please pause this video to find out. Now that you found out that this radius, this new radius, is half of the original radius, all we really need to do is some equation manipulation to find our answer. So, working with our formula, f of g equals gm1 m2 over r squared. If we have half of the radius now, what happens to f of g? Well, like we talked about in our equation manipulation worksheet, if we half the radius, whatever we do to the radius, we have to square as well because the radius is squared. So you end up with 1/4 r squared. 1 squared over 2 squared is 1/4. So we don't like fractions and fractions, so what we can do to that is flip it over, multiply by the reciprocal of 1/4, which is 4 over 1, and that will get rid of that. Now we're changing the original equation by 4 times. So we need a 4 times the force of force to gravity, force of attraction. So if the original force of attraction was 2 times 10 to the 30th newtons, now it's 4 times that amount. 4 times 2 times 10 to the 30th newtons. 4 times 2 is 8, so it's 8 times 10 to the 30th newtons as the new resulting force, which is choice 4. I want you to try this question on your own. You can ignore the electrostatic force. They both have an inverse squared relationship, so we really just need to look at the force of attraction, the gravitational force, to find out which answer is correct. So you try it out. You have a distance of 1 meter between the two objects. The objects, the distance between the spheres is increased to 3 meters. So if they change the distance by a factor of 3, they're asking what happens to the force of attraction. Pause the video now and work on this question. Hopefully you see that if we triple the distance between the two objects, that this 3 is now squared, becoming a 9. And if I bring it out of my original equation is 1/9 the original. So f of g is also 1/9, or f of g divided by 9, which is choice 1. The electrostatic force has a very similar equation where there's an inverse squared relationship between distance and electrostatic force. So no need to worry about that now, but this is our answer. The next question, a small planet, an astronaut uses a vertical force of 175 newtons to lift an 87.5 kilogram boulder at a constant velocity. You know what that means? To a height 0.350 meters above the planet's surface. What is the magnitude of the gravitational field strength on the surface of the Earth? When they ask you about gravitational field strength, all they're asking for is gravity. What is gravity on the surface of this planet? So we need to know 2 things. We need to know the force of attraction, or weight, and we also need to know the mass. So we know if the object is being pulled up with a force applied of 175 newtons. We know that the weight downward must be equal to that, since it's moving at a constant speed. The height of the boulder is not important in this question. The mass of the boulder is given to us as 187.5 kilograms. So take a minute, pause the video to do your math. The weight of the object, 175 newtons, divided by the mass, 87.5 kilograms. So you should have found that g is equal to 2 meters per second squared. However, they express the answer in newtons per kilogram, which is fine. Those are the units in our work. Remember that gravitational field strength and gravity are the same thing. This next question foreshadows what we'll be talking about in our next topic, which is circular motion. So a space shuttle is orbiting the Earth. So if this is the Earth and this is the shuttle, it's orbiting around the Earth. And no, I'm not going to draw any perfect circles on this video lesson. So they say that the centripetal force acting on the space shuttle as it orbits the Earth is equal to the what? Centripetal force is a force that keeps an object in its circular path. So it's always acting inward to the circle, keeping the object in the circular path. So it's okay if you don't know that. We're going to talk about it next topic. So what is this force that's acting towards the center of the Earth? Well, you should know that the force acting towards the center of the Earth will always be the weight of the object. Please go to your Prentice Hall books and work on page 64, the following questions.